talk about would be lubrication and journal bearing. So last class, what we did was we looked at bearings which had rolling elements in it, right? So this one is something called journal bearing. So before we start, I would like to understand from you, do you understand what a journal bearing means and how is it different than a ball bearing? Fundamentally, is there a difference between a journal bearing and a ball bearing? And what do you think is the difference? Anybody has heard about journal bearing before? Any of you can just type your thing in the text box, or you can unmute yourself, whatever you feel comfortable with. So if there is already a way to have a bearing, there is another class of bearings called journal bearings. The first question is, have you ever heard of this journal bearing? First question. Anybody? None? Nobody has ever heard of journal bearing? Okay. So my question is, let me just give you an idea what journal bearing is. Journal bearing is nothing but a shaft and a sleeve. And in between the shaft and sleeve, there is a fluid film. So you add some viscous fluid between a sleeve and a shaft. How many people know what a sleeve is? Everybody knows what a sleeve is, right? Sleeve is just a cylinder kind of a thing. It can be either partial cylinder or a full cylinder in which the shaft will rest. Now my question is, if I have those ball bearings, right? I have those ball bearings, I have those roller bearings. Why would I want a mechanism like this, where there is just a sleeve with a lubricant? Is it very effective? Would we want something like this? Yes or no? Why would we want something like that? Any ideas? It looks simplistic to me, right? Easy to install. I don't know. Easy to install. Bushing may be easy. Yes, you just want bushing, it's easy. But is there a fundamental benefit of using those kind of bearings? Easy to install is okay. It's a decent point. Alignment. So let me ask you to do a thought experiment for you. What if the speeds are very, very high? If the speeds are very high for, say, small bearings, very, very high, say 80,000, 90,000 RPM or some crazy speeds, right? What do you think will happen to ball bearings? What would happen to ball bearings? Any answers? If the speeds are very high, there will be a lot more friction between the ball and the races, right? What will happen? If there is a lot of friction, it's rotating at very high speed. So even if the bearing reduces the friction, if it rotates at very high speed, there will still be friction between the ball and the race. And because of friction at very high rotational speed, what do you think will happen? What does friction do? Heat generation. Very good answer. So heat generation. And what the heat generation will do? Finally, what will heat generation do? If the bearing gets very hot, what do you think will happen to the bearing? If bearings get really, really hot, you use very high speeds. Thermal expansion may be, there will be thermal softening of the material and the bearing seizes. The bearing will seize means bearing will stop to function. It will plastically deform. Right? So fundamentally, there is a limit to what speeds you can use a rolling element bearing. You get me? Now, if you have very, very high speeds, you have to do something else. So that's where a journal bearing is coming. Let me just first give you start with a small, what do you call, small YouTube thing, and then we will move to today's class. Okay.
Journal bearings typically consist of a metal sleeve that fits around a shaft. The sleeve is held in place within a housing. The journal is simply the place on the shaft that is surrounded and supported by the bearing. Journal bearings can be made out of metallic or non-metallic materials. Examples of common metallic bearing materials include bronze and brass. This example of a non-metallic bearing material is called phenolic. This fibrous synthetic material is used in power-generating applications because it does not conduct electricity. Another common bearing material is called babbitt. Babbitt is a soft alloy comprised of tin, copper, and antimony. Babbitt is usually bonded to a shell of harder metal to give the bearing strength. Bearings are generally made out of material that is softer than the metal of the shaft. This helps to protect the shaft by allowing the bearing material to wear out first. Journal bearings usually have a lubricant groove on the inside surface of the bearing. This groove generally runs parallel to the shaft and helps distribute oil and grease along the shaft when the shaft passes through the bearing. There are two basic types of journal bearings: solid journal bearings and bearings. Solid journal bearings consist of a solid one-piece sleeve mounted in a one-piece housing. A solid journal bearing is sometimes called a bushing or a sleeve bearing, depending on its thickness. A bushing is a relatively thin, solid journal bearing that gets most of its strength from the housing in which it is mounted. The term sleeve bearing generally refers to a thick-walled journal bearing. A split journal bearing consists of a two-piece bearing mounted in a two-piece housing. The advantage of a split journal bearing or a solid journal bearing is that it can be separated into two halves. A split journal bearing is easier to service since it can usually be separated and removed from around the shaft without removing the shaft itself. Solid journal bearings can be more difficult to replace than other journal bearings. Frequently, it's be slipped on and off the shaft, or the shaft must be removed through the bearing. Journal bearings typically consist of a...
Okay, so you guys know what journal bearing is, so I'll just stop here and then start sharing my today's class. Okay. So it looks like there is something going on. Till I figure it out what went wrong, I'll start with this. Oh, just 1 second, let me start sharing the screen. I'm going to share this and then I'll share it. Looks like there is some issue. Good. So I think it is being shared. Somebody, looks like somebody has to mute themselves because there is some disturbance coming. Okay. So what I'll do is I'll start the class today. Okay. So today's class would be primarily about lubrication and journal bearing. So these two go hand in hand, lubrication and journal bearing, right? So what do you understand by lubrication? What does lubrication mean? And how does lubrication work? First question would be, what does lubrication mean? Lubrication mean? And how does it work? Working principle. Can somebody tell me? What does lubrication mean? Somebody must know lubrication, right? You talk about lubrication at every single instance, right? Everywhere you guys talk about lubrication. What does lubrication mean? Somebody? Like your mechanical engineers, you would have sound understanding of what lubrication means, right? Some answer I would like to have about lubrication. Very good. Reducing friction. I think that's bang on target, right? Reducing friction is the perfect answer. Lubrication reduces friction. Now, can someone tell me what does it do to reduce friction? How does it manage to reduce friction? That's the perfect answer. Lubrication reduces friction. But how does lubrication manage to reduce friction? What does it do that the friction goes down? Forms a thin layer between the contacts, right? So there is a thin fluid film between two contacts. Typically, if you imagine any surface is rough, right? There is nothing called smooth surface. It's just that at what level you are watching. To you, it may appear very nice. To you, it may appear it's very smooth. But at the microscopic level, at whatever scale there exists some, the smoother, the lower the scale. But still, it will have some asperities. So origin of friction is basically a couple of things. What will happen is these high points, if there's a relative motion between the two, this asperity, the high point, will basically interact. So there will be mechanical interlocking. There will be mechanical interlocking at a very small length scale. Mechanical interlocking will be there. This will create friction, or there will be adhesion between the surfaces. So there will be some adhesion, right? There will be some sticking between the surfaces. So mechanical interlocking and adhesion cause friction. Now, if I introduce a fluid film here between the two, so this fluid film will separate these two. I'll tell you why it separates. If there is a film, why it separates the surfaces. But now what will happen is there will be the friction reduced because the friction is because of only the shear stresses. If there is a full film lubrication, if it's a full film lubrication, if the lubrication separates both those surfaces fully, there's full separation, then there would be lubrication due to only the friction will be only due to shear stress in that fluid layer, which is significantly lower than mechanical interlocking and adhesion, right? So friction is primarily because of interlocking of asperities and adhesion. And if you introduce a fluid film there, it will basically reduce friction because now the friction is primarily because of the shear in the fluid, which is much, much lower. This is what we'll analyze today a little bit, right? So journal bearing and lubrication are very closely linked. Okay. Now I'll talk about first thing is what kind of lubrications are there? What are the regimes of lubrication? Then I'll talk something about viscosity, and we'll deal only with Newtonian fluid. We'll not do it with non-Newtonian fluid. Although most of the things which we use in bearing lubrication are probably non-Newtonian, but we'll not go there. We'll do first order approximations as we always do. So we'll do some first order modeling here using Newtonian fluid. Then we'll talk about Petrov's equation. Then we'll talk about thick film lubrication and something very interesting about what's called hydrodynamic theory. And it is an equation called Reynolds equation. It's a very interesting piece of equation. And there are people who have been solving entire lives Reynolds equation of different form or shape with different level of complexity. And we'll solve this Reynolds equation today and show you how the Reynolds equation, we'll not solve, but we'll formulate the Reynolds equation to show you what Reynolds equation says. And there's a very interesting reason why somebody investigated and got this theory. So what had happened was that initially people were making this for rail shafts, they were making these journal bearings. And what was happening is the moment the axle rotated, there was a plug on the bearing pot where the bearing had a sleeve, and there was a fluid film in that sleeve, and then there was a cap. The cap will just pop out. So they were not able to understand why this cap was popping out. I will tell in detail that story. And finally, they tried to figure out why was it popping. And then they figured something is happening, and they commissioned an engineer to investigate it. And Reynolds was commissioned to investigate why this was happening, and he figured this out. So it's a very interesting story which I will share as we go there. So basically, we know lubrication reduces friction. Sorry, it reduces friction. The first task of lubrication is reducing friction. And if friction is reduced, there will be less wear and the heat will be less, because friction inherently will cause heating, right? Any energy which is generated will end up being in heat. So if friction, the frictional heat, the frictional energy which goes will become heat. So that is the thing. So friction basically will inherently heat. So if you reduce the friction, there will be lower heat and lower wear. So this friction, wear, and lubrication, these three terms created a new field called tribology. This was in late 50s, early 60s. This field came, and this field was called tribology, and all it does is it studies friction, lubrication, and wear. Okay. So what we will talk today would be, there is a shaft or a journal which rotates on a sleeve or a bushing, and there's a relative motion. And journal bearing, so most of the things, if you see, there is a chart which I'm showing you here. What happens is the bearings, which are rolling bearings are operational here. This is the regime for rolling bearing. This is the regime for this. All this is rolling bearing. All this is rolling bearing. So this is the rolling bearing regime. This one. Now this is a regime where these things you see, right? This regime is where you see very high speeds. These are, so rotational speeds are very high, right here. 10,000 revolutions per second means 60,000 RPM, right? Very high, very high rotational speeds. You go to this kind of a mechanism which is called journal bearing, because the steel bearings may seize, they may soften and seize, they may not be operational. The kind of heat which will be generated will render it useless at that rotational speed. So this kind of a mechanism, this kind of a bearing, which is a journal bearing, comes to a rescue. So journal bearings are for extreme conditions, very high loads and very high speeds. High loads and high speeds. High speeds. So typically you see here, they say about 10,000, 100,000. 100,000 revolutions per second means 100,000 revolutions. They haven't shown anything here, because if you see, there is nothing. This regime, there is nothing. So can somebody tell me what kind of bearings we use in this regime, where there is nothing? If I have to operate in this regime, say, can I use a bearing here? Any ideas? So this area for number 1 is ball bearing. This number 2 is journal bearing. What do I do in number 3? This regime. Any guesses? Very high speeds. Let's not worry about loads as of now. Good answer. Air bearing. The only challenge will be you may not be able to support a lot of load. But for very, very high speeds, there is something called air bearing which people use because the friction is even lower. Right? So this is not shown here, but that's also a sort of I would say a fluid bearing only, right? It's just that there is a compressible fluid instead of incompressible fluid. Okay, so this is what I wanted to give you a regime for different bearings. Now let's go to different kind of lubrication. The first regime is called hydrodynamic lubrication. How many people have heard of hydrodynamic lubrication? You have heard about hydrodynamic, right? Why do you call it a hydrodynamic lubrication? You can read it. It says the surfaces of the bearing are separated by a thick film of lubricant. The fluid flow due to moving surfaces in a converging gap, which generates pressure separating the sliding fluids. So this is a very interesting concept. This hydrodynamic concept is what happens fluid flows in a converging gap. There is a pressure built up which separates this. So there is a pressure. So if there is a load and the fluid is flowing into a converging gap, this will push this. The pressure will be created into the fluid film, and it will support load. So there is no external pressure, right? You're not providing external pressure by virtue of how the fluid is moving, because what will happen is one of the surfaces is in relative motion to the other, right? So this will be drag the fluid. This will drag the fluid, right? So there will be a fluid flow because of the motion of the. So if we assume that there is no slip boundary condition, so the velocity here, the velocity at the base would be 0, and the velocity at the top where the surface is moving will be whatever the velocity of the surface is, say u, right? So what is happening is the fluid is being pushed into a converging gap by virtue of the relative motion, and this action will create pressure in the fluid, and this pressure will support load and give you a bearing action. This kind of a phenomenon is called hydrodynamic phenomenon. Hydrodynamic, and this is the basis. This is the basis for your journal bearings. Okay. Now there is a hydrostatic bearing where what you do is you put a pressurized lubricant in the bearing, and that will the pressure will sustain the load. So, but then you need some sort of a pump to pressurize the lubricant and bring it in. There is another concept which is called elasto-hydrodynamic, EHL. There what happens is there is, say, in rolling bearing or roller bearings in gears, what happens is there's a fluid film between the two, but the pressure between the two happens in a converging gap, and what happens is the pressure is so high that there is elastic deformation also. Elastic deformation because of the contact. So there is a contact elastic deformation and the fluid pressure together. So the pressures are so high, contact pressures, is that there is elastic deformation of the surfaces, and there is a fluid film. So the combination of elastic deformation plus hydrodynamic is called elasto-hydrodynamic lubrication. Any questions here? I'll just wait for a little bit. If you have any questions, ask me, and then we'll move on to the next thing. Any doubts about hydrodynamic, hydrostatic, or elasto-hydrodynamic? Anybody? Okay. So you got it, then we'll move to the next thing. There's something called boundary lubrication. Boundary lubrication is very interesting. There what happens is, typically up till now we are assuming that the surfaces are smooth. right? We are assuming that surfaces are smooth and then there is a fluid film between the smooth surfaces, right? Imagine that if you have a very small clearance, the separation between the surfaces is very, very small. In that case, what will happen is your asperity will start to interact. Your surface roughness will start to interact. In that case, what will happen is there will be fluid film and there will be these asperity to asperity contacts, and this has to be modern. So this is called mixed or boundary lubrication. Mixed lubrication where surface phenomenon is there. So mixed lubrication is a step above boundary, where there is the effect of surface roughness. So surface roughness is not getting in, asperities are not interacting, but the effect of the roughness is there on the fluid film. Boundary is a step ahead of mixed lubrication, where there is actually interaction of these asperities. So if you have these surface, right, surface will be a rough surface, something like this. There's another surface. So these will interact. These asperities, the high points will get to interlock with each other, and that has to be accounted for. Okay, so that will be boundary thing. The next class of things is you actually create a solid coating on the mating surfaces, like graphite, tungsten disulfide, molybdenum disulfide, and this dry lubrication. So there will be no fluid, but this dry coating will have this lubricant property. So these are used at some of the conditions. You have where what happens is very high temperatures where the viscosity will become very low. So what you do is you use solid film lubrication. So you coat that with lubricant. So these are the type of lubrication schemes which you use. Okay. Any questions now? Okay. If not, let's move to the next thing. Okay. Viscosity. So before you go to viscosity, can somebody explain what viscosity means? Because you have done fluid mechanics, right? So you know the concept of viscosity. What does viscosity mean? This I expect an answer from you folks, right? Because this is something which you know very well. What is viscosity? Anybody? Because you have done fluid mechanics 8 credit course, right? You better know about it. So there are 25 people. I'm sure a big bunch of people knows what viscosity is, right? Somebody has to tell me. Force due to shearing of fluid. Force due to shearing of fluid. Okay. So if I ask you another question, if I ask you what is modulus of elasticity, what do you say? What is modulus of elasticity? Those answers are right intuitively. Force due to shearing of fluid. Yes. When shear happens, something happens, right? So if I have shear, right? Shear is proportional to, let's say, du by dy, right? In mechanics, if you do, you say sigma is proportional to strain, right? Resistant to shear fluid. That's a very good point. But I want you to appreciate what mu is, viscosity is fundamentally, right? So you have tau, and tau is proportional to strain rate, shear strain rate, right? Do you see a similarity between stress and strain and shear stress and shear strain rate? This is a constitutive relationship which relates some state variable in fluid mechanics. So the key things in fluid mechanics is that your shear stress, like in mechanics, the stress is proportional to strain, right? And this proportionality constant is modulus of elasticity, which is nothing but the stiffness. Similar thing, you are right. It's a resistance to shearing of fluid. Some stiffness to shear. Right? That's exactly what it is. This is also a constant relationship, a constant for constitutive relationship. Very similar to what you do in modulus velocity. This is exactly the same. So basically, tau is equal to, when you say, so here instead of strain in fluid, its strain rate is important because fluid is a flowing thing. Even in metals, when it's in the flowing phenomenon, strain rate becomes related to the stress, not the strain. So when there is physical material movement, strain rate is the important, what I would say, it is called a state variable. So this is what affects the shear stress. Shear strain rate affects the, this is nothing but, this du dy is a shear strain rate. Shear strain rate, which is basically u over h in this case, because it varies from 0 to u, and tau is the shear stress in the fluid. And if it's a full fluid thing, this is what governs the friction for a full fluid thing, right? So tau and this mu is nothing but the proportionality constant, which somebody very rightly pointed out. It's the resistance to shearing of fluid, resistance to shear, right? How easily it will shear is governed by mu. If mu is very high, it's difficult to shear it. If mu is low, it's easy to shear. It's exactly something like what is modulus of elasticity. If it is E is high, it's difficult to deform. If E is low, it's easy to deform. Exactly same thing. This is a constitutive relationship for, so instead of mechanics, there's a conversion. This is a constitutive relationship for fluid mechanics, right? Now I have these tau is equal to mu du dy. I'll use this. Although, let me give you a disclaimer. This may not be very accurate for the fluids we use in bearings. But still we'll use it because this is easy to handle. This will give you good estimate. It won't give you the perfect estimate, but it will give you a decent estimate even if you use that. Okay. So viscosity, now you understand. Now what happens is, this is how the viscosity temperature diagram looks for different materials which you use in bearing applications. Castor oil, SF oil, if you see, with temperature the viscosity changes. And higher the temperature, lower the viscosity. Unfortunately, this is true for not all materials, but water shows less, but most viscous materials, the viscosity drops with temperature, right? That is there, but I'm just giving you this. So there will be some operational limits on every viscous fluid. So whatever viscous fluid you use in your bearing, there will be some operational temperature for it. So what do you do? How do we ensure that the temperature remains within the limits of the viscous fluid which you are using? What should we do to the bearing? So each oil, so let's say this will have this zone. Castor oil and SA30 you would have between here to here. After that, the viscosity goes down significantly, so you will not get the shear. Okay. So what do we do? What do we do to make sure that the bearing remains in that zone, in that temperature zone? It doesn't really get heated. Simple answer, right? What do you need to do? This is an important aspect. Most of the bearings which are operating at reasonably high speeds are cooled. So bearing cooling is an important aspect because you cannot let the bearing overheat. Bearing cooling is a very important aspect. especially high-speed bearings. So I have a high-speed spindle which I use in my machine. The spindle is hardly 2 inches by 6 inches size. This is the spindle size. Probably this is what I am showing. This is the size of the spindle, slightly longer than this. And the chiller to cool the bearings in this spindle are 250 kgs. Just to give you a weird example. To cool a thing which fits in your palm, you need a cooling device which is 250 kgs. Funny, but true. Okay. Okay. Any questions here? If you have any questions, we'll stop and then answer the question, and then we'll move on to the next thing. Any questions here? You guys have any questions here up till now? None. So let's move to the next thing. So there's something called Petrov's equation. Petrov's equation gives the coefficient of friction in general bearings. This is how you find with Petrov's equation. It assumes that journal and bushing are concentric. This is not true. Let me tell you a priori, this is not true. But still, this estimate which we will use, we'll formulate this problem. This gives a reasonably good estimate of friction. Even though it is not concentric, we'll assume this to be concentric. So now let's see how the things look. So there is a sleeve. So this is, if you see here, there is a fluid film. This is a fluid film. Concentric fluid film. The pink one. Right? The pink one is the fluid film. Now what will be the shear stresses here if I assume tau is shear stress, fluid stresses is tau. So how do I estimate what will be the total frictional force? Can somebody help me here? Tau. So tau is equal to what? Mu u by h, because I'm assuming that it is 0 at the sleeve and maximum at the journal. At the shaft, it's the maximum velocity u, which is 2 pi rn or pi dn, right? Tip velocity or peripheral velocity. So tau is there. What will be total frictional force? Frictional force, if I want to find out, frictional force F will be equal to what? Tau, or let's say I want to find out torque, total torque due to frictional force. Torque due to frictional force. So this will be tau times A, right? This will be tau times A. Whatever is the contact area will be the frictional force, right? Right? Tau A is force, frictional force, times this will be R. Tau is equal to mu. Tau is equal to mu. U is what? Mu u by h. U is 2 pi Rn. Sorry. Do a good job of this. Mu. U is 2 pi Rn. N is the RPM. Right? Pi dn or 2 pi Rn divided by h. Or I will use clearance here C. H is basically the height, which is C clearance here. Here I'm using the clearance C as a term, which is the difference between the two surfaces. Right? So this is tau, and A is what? A is nothing but 2 pi RL, the curved surface, times R. So the frictional torque due to friction would be equal to mu 2 pi R, right? N C 2 pi R square L, right? So this is the torque due to the fluid. Now, I can equate this, right? There is I know the weight it is supporting, right? If I know the weight it is supporting. So I know that the frictional force will be W is the load, right? So what will be the friction force? Mu friction times W will be frictional force, right? Frictional force will be this. FF will be mu times W, mu F times W, right? Mu F is the coefficient of friction. I'm not using mu because mu I'm using for viscosity. So I'll use a better term. I'll just use F here. Coefficient of friction, small f. So F times W is frictional force. Now what will be the torque due to frictional force? This torque. Mu F times R, right? So F, W, R is the torque. Frictional torque. Right? So coefficient of friction, if I have to find out, can I equate these two? I know. Let me equate these two. So F will be equal to, coefficient of friction will be equal to mu times 2 pi, or actually 4 pi square. Let's see, 4 pi square, right? 4 pi square R cube, right? N L divided by C divided by WR. Agreed? Agreed? Everybody agrees to this? I know you guys do much better job of calculation. So just cross check whether this is right or not. So I equated the frictional force due to the fluid film to the effective friction, right? So the torque should be equal, right? The frictional torque should be equal to whatever the shear fluid, whatever is the shear stress there, because that is the one which is giving the torque. The friction is coming because of shear stresses. So I can basically estimate what will be the coefficient of friction. Now, if I know the pressure, can I find out what will be W? So one way to estimate would be W will be nothing but P times the pressure times projected area. Projected area is what? If you look from top, what is the projected area? 2RL, right? The diameter times the length. That is the projected area. So I can basically put this term here as P times 2R times L. Now you go ahead and cancel all this, whatever needs to be cancelled. 2 will become 2. This R cube will become 2R. This is P into 2RL into O. Okay. So this will just become R here. So this is R square. So this will become R here. L will get cancelled. So effectively, what you will get would be mu pi square R N divided by PC. Let me go to the final equation. So basically what I get is F is equal to 2 pi square mu N by P RC. I'm writing this by design this way. So there are two terms here, mu N by P and R by C. These are the two important terms actually. And this equation, this frictional force, will be a function of your clearance, your radius, your pressure, and your RPM. And of course, viscosity, which is. So this coefficient of friction can be predicted by Petrov's equation. And this is reasonably accurate. Okay, so the question somebody asked is the friction here would be between the fluid and the journal? The question is the total friction which is happening now. Where is it happening? How is the friction originating? What is the origin of friction here? The friction between the fluid and the journal? So this friction, when you talk about, right, you always talk about two meeting surfaces, right? This is what is there in your head up till now. Right? Friction is between two meeting surfaces. Now, the friction between two meeting surfaces now is reduced to just the shear in the fluid. Get your head out from two. So those two things become unimportant now because there's no physical contact between the two, right? So the only thing that remains is the shear in the fluid. So the friction here is not between the fluid and the journal, but just in the fluid. The entire friction is coming because of the shear in the fluid. Whatever shear stresses are originating, that is the friction. That's all alone is friction. And if you want to understand logically, the friction is still between the two surfaces. The friction is still between the journal and the shaft, the journal and the sleeve, or the shaft and the sleeve. That's the friction between these two surfaces. But unfortunately, nothing is happening between these two surfaces are physically separated. So whatever action is happening in the fluid film. So the friction is originating because of the shear in the film. So friction is still happening between those two meeting surfaces. But if you want to understand how it is originating because of shear in the fluid. Just shear in the fluid. So your question. Yeah,
मागे तो टेस्ट और एग्जाम में मेरो सेमेस्टर को की कौन सा साल भेजा एग्जाम होते हैं सेमेस्टर एग्जाम
somebody okay, sorry for the disturbance. Okay, so you understand the friction is still between the two surfaces, but it is happening only because of shear in the fluid. That's what I wanted to kind of bring out. Okay, so this is what is there in Petrov's equation. The Petrov's equation, even though it assumes incorrect formulation, it's not concentric, but still it will give you the right answer. Okay, for friction. So there are two dimensionless quantities, mu n by p and r by c, which are extremely important. This you have to understand. And there's something called Sommerfield's number. Sommerfield number, and Sommerfield number we'll go and discuss again one more time when we cover the equation. This, what is it called, the Reynolds equation. So Sommerfield number is r over c whole square mu n by p, and this is actually one estimate of Reynolds equation, which will go there. We'll go when we'll talk about it. I'm just priming you right now. Okay. Okay. So there is something called stable and unstable liquid. So there's a film thickness which is important. So what happens is, if I have very thin film, the coefficient of friction increases because there will be a lot more asperity to asperity interaction and adhesion. Asperity to asperity. So these points, if you see at micro scale, these points will start to interact. These high points. So these high points of the surfaces would start to interact, right? So at smaller film thicknesses. So these are inherently unstable, but beyond a point, you will become the fluid film will full film will take place, and there would be stable zone. So wherever the minimum friction is there, this is the transition point where the transition goes from metal to metal contact or asperity to asperity contact to full film contact, right? And the common design constraint for that point is mu n by p at that point is greater than or equal to 1.7 to 10 to the power 6 minus 6. Okay. Now, if you have the dry contact, see, this is the sleeve, this is the shaft. You have a whole Q flow here, material is flowing, and then if you go ahead and rotate, the fluid is flowing into a converging gap, and there will be pressure build up. Pressure build up. So I'll explain what is the bearing nomenclature before we go ahead and do it. So this is the center of the O dash. O dash is the center of O dash is the center of bearing is O dash. This is center of bearing O dash. The entire bearing. O is the center of journal. So O is the shaft center, and they are eccentric. If you see that there is eccentricity, which is E, and maximum film thickness occurs at the line of centers. Okay, and then what happens is the fluid starts to flow in a converging gap. So what will happen is there will be a gap which will converge, keep on going smaller. Partial bearing is about 360 degree, less than 360 degree, and full bearing is the entire complete sleeve, right? And there's something called eccentricity ratio, which is E by C. Fitted bearing has equal radii, so the radius is equal of the sleeve and the shaft. That's called fitted bearing. So now what I will do is this is just to give you the geometry. There is always an eccentricity in journal bearing. This is what I wanted to highlight. Journal bearing always will have eccentricity. Journal bearing will have eccentricity because we want to have flow in converging gap, which will create pressure and sustain the loads. Converging gap, it will create pressure and sustain load, meaning it will start to act like a bearing. It will start to act like a bearing. Right? Now there was a very unique experiment in 1830s. These are called tower experiments. So this was a railroad bearing in 1880s, and this one guy, he made a what is it called, a sleeve to hold the railroad shaft, right? And what he would do is he would fill it with fluid and then let the wheel rotate, let the shaft rotate. The moment shaft would rotate, there will be fluid which will come out of this. The moment start rotating, the fluid will come out of it, and you lose fluid. Then what he did was he tried to first use a cork. So he used a cork. Cork, you know, right? Cork is like the wine bottles which you have seen, right? That plug. It's a light. It's a very light density wood. So he put a cork and put the cork. Again started rotating. The cork popped out. The cork popped out. He was very surprised. Why is the cork popping out? Then he went ahead, took a wood piece and hammered it in. So initially he did nothing. Fluid came out. Then he went ahead and put a cork there. The cork popped out. Then what he did is he went ahead and took a wooden plug and hammered it in. The wooden plug also came out. The wooden plug just popped out of this. Now this fellow was saying, what is happening here? The moment it's stationary, nothing happens. The moment this journal starts to rotate, that thing will pop out, right? And he was very surprised. What is happening? Why is this happening? He could not understand, right? So they went ahead and commissioned Reynolds to figure out what is happening. Why is this happening? So somebody went ahead and so Tower actually figured that there is something wrong, but he did not have a physics to prove the point that what is happening inside which is doing this kind of a phenomenon. It's a very interesting phenomenon which is happening, but he just didn't have an answer to that. Okay. So what he did was he said that let us try and see why this is happening. But he pointed out that this Tower pointed out that there is pressure generation the moment it rotates, but he could not figure out what the physics is. Then they had Reynolds. Reynolds was a big guy then. He was commissioned to figure out what is happening. So this is what he formulated based on that commissioning. He said that the fluid films were thin in comparison to bearing radius, so curvature could be neglected. So he basically found out that the matter is that that the fluid film is very thin and curvature is very large. So we can assume this to be a basically a straight kind of a thing. We can assume that this is a straight thing, albeit with a flowing converging gap. Right. So what is happening is we can assume that there is a fluid flow in a converging gap. He figured that out and then said that he can assume it to be straight for now because the thickness to the curvature is very large. Right. So what he's saying is that you can assume it to be straight for all practical purposes. Then he said that he made a free body diagram of this, which is if you assume that this is x, if you assume this is y, and z is perpendicular to the shear. So this is P. Sorry, my mistake. This is P, right? And the area here will be dy dz, dy dz. This will be P, since it is in del P del x direction. P plus del P del x dx, right? And so I'll just write it properly here. So P plus del P del x dx times dy dz. So fluid pressure is acting. It's pressurizing from both sides, but there will be pressure difference because of the gradient, pressure gradient, right? Now shear, if you imagine what is the velocity here? So this is moving with u, velocity u. This is moving. This is what is happening here to the fluid. What is the velocity there at this location? What is the velocity of the fluid at this location? Somebody, what is the velocity of the fluid at this location? 0. Very good. And here it is maximum. So shear, what will happen is this portion, the shear stress is pushing it forward. Here it is kind of impeding, right? So what I will do is I'll put shear, the shear here and shear here like this. The shear, if I want to say here, is tau dx dz, and this is tau plus del tau by del y dy dx dz, right? And pressure I have already figured out, right? So can I do the force balance here for these elements? So let me do the force balance for these elements. Sorry. The force balance will be, if I say, so this will be, the force balance will be very simple. I add these two, and these two will be equal, right? So the positive and negative, let me do it. So I say sigma fx I do is equal to 0, which basically means P dy dz minus P plus del P del x, right, dx dy dz. This is the pressure one, minus tau dx dz. If you go ahead and see, minus tau. So this is negative, and this is positive. Okay. Minus tau dx dz plus tau plus d tau. Tau plus del tau del y dy dx dz is equal to 0. Expand this, right? So you will be left with del p del x dx dy dz. Say dx dy dz is equal to del tau by del y dx dy dz. So what I will get is del p, I'm sorry for this, I will get is del P by del X is equal to del tau by del Y. This is the equation I get after the balance, right? So what happens here is I assume that del P del X, P is only a function of X. P doesn't depend on Y. This is my thing. So I can say del P by del X is nothing but dp dx because it's only P is only function of X. So I can say dp dx is equal to dp dx is equal to dp dx is equal to del tau by del Y. And if you see dp dx is tau is what? Del by del Y. Tau is equal to mu del u by del Y. Del u by del Y. So I can basically get this equation. The differential equation would look like dp dx is equal to mu del 2u del y square. Right. This dp dx, if you think about it, assume dp dx is just the pressure gradient. This is a pressure gradient, right? dp dx. So I can basically assume that my 1 over mu pressure gradient dp dx is equal to times first thing will be del y is equal to del by del y mu del by del u del by del y. So del u by del y. This is what you get, right? Sorry. You know all this, so I'll just go quickly. So del u by del y will be this. So if you del u by del y, right? So if you do first integration, you will get del u by del y. You get, and then what you get would be 1 by mu dp dx, the pressure gradient dp dx y plus c1. This is what you get after the first integration. After second integration, you go ahead and do that. Simple. You will get something like this. You will get something like you do y square by 2 and c1y plus c2. Right? What I can do is I can basically find out the boundary conditions. So the equation which I have, let me go ahead and write the equation here. U is equal to let me just go ahead and write the equation here. U is equal to 1 over 2 mu pressure gradient dp dx dp dx y square, right? Y square plus c1 plus c1y plus c2, right? This is the equation. Now I can get these. I know the boundary conditions at y is equal to 0, u is equal to 0, right? Which means c2 is equal to 0, right? And at y is equal to h, u is equal to u. So I can plug that. So basically u is equal to 1 over 2 mu dp dx, right? H square plus c1h, right? And c2 is 0. So I can find that c1 is equal to u by h, right? Minus h by 2 mu dp dx, Agreed. So the final equation after basically putting in the constants will be u is equal to 1 over 2 mu dp dx y square minus hy plus u by hy. So this is the velocity u as a function of y. This is the solution u as a function of y. Right. Which basically means if dp dx is equal to 0, u is equal to u by hy. Look at if dp dx put 0, so you will get a very nice linear term. So at 0, you get a linear term. If my dp by dx is equal to 0, it's a straight line. If it is greater than 0, it comes like this. If it is less than 0, it comes like this. That will be the nature of flow. This is how the flow will occur. So velocity as a function of h is something like this. Okay. So what I will do is I will not go any further. We have 3-4 minutes left. Or how many minutes left? No, about 7-8 minutes left. So what I will do is I'll stop here. We'll take this stuff in the next class. There is something more which we will do. We'll basically try to find out what will be the flow. Right? How do I find what will be the flow? Q. How do I find what Q will be? Any answers for that? I know U is a function of Y. Can I find out what will be the function? How will be Q? What will be the Q? Assuming that the side is linear or unit. So basically this, what is it called? The Z direction is just unity. Let's not worry about Z for now. How would I find out what will be the flow? Entire flow. Very good. Integrate with dy and find out. Very good. And how will it change? Will the flow change? Assume this is incompressible. What will happen to dq by dx? What will this term be? Will the flow change as we go along x? This is x direction. Yes or no? Think about it. Now what I want to do is we will do the Reventer formulation in the next class and derive the entire. So this is one portion which we have done. I don't want to rush today. So we'll take this in the next class. I want to ask when do you guys want to have the project presentations, the final one, and also I want one more intermediate presentation. 2 things I want. One intermediate presentation and one final presentation. 2 more presentations I would like, and then final report. There will be 3 more things which you have to do on the project, and it's 50% of your grades. So you do it with all your efforts. That would be appreciated. So I have 2 choices. We can do it the next Wednesday. That's one option, or the Wednesday after. So I think next Wednesday would be what, 5th, right? 5th or 11th. What would you prefer? Actually, that next will be, let me see, November 4th, right? 4th or 11th, right? 4th or 11th, sorry. 4th or 11th. Which one would you prefer? So I'll send out an email, but what would be your preference? 4th presentation you want to do on 4th or 11th?
Hello, sir.
Yeah.
So if it is on 4th, then that will be the intermediate presentation, right?
Yes, 4th is intermediate, and the final one I'll have you a call. Whether you want to do it after the exam, before the exam, it should be your call. I don't care regardless. All I want is 4 to 5 days before the grade updation, before the grade uploading, because I would like to go through your reports and grade it. That's the only
question. by when, so if we are having it after the NSIMS, then by when we have to submit our reports?
4 days before the grade updation. Because I need to grade it, right? So I would need at least 4 clear days to go through your reports and give you a grade for that.
Okay, sir.
Okay. But that you guys have to figure out when do you want to do it. Would you prefer after the exam or before the exam? What would you prefer? I'm okay with either. So Ujjwal, are you there or you're not there? Ujjwal, are you there? Looks like
So I think so Ujjwal can take a poll on the group and then let you know about it.
I'll shoot an email to you folks. I'll actually tell that these are the options and then you can have your pick.
Sure, sir. Sure.
So with this, if you have any questions, I'll be happy to answer them. I still have a couple of minutes left. If not, thank you for joining this class and we'll meet Monday. So I'll still be around. You can ask any questions if you feel like.